Okay, so we just finished 2.2 last time. Separate equations that you can separate the variables into the two sides and then integrate different variables on the two sides. Separately. So that's a relatively straightforward differential equation. Although sometimes you may not be able to actually integrate the function, at least you can find out or write down the solution of the differential equation in an integral form. So that's a very special case. Today we're going to discuss another simple case of differential equations that we can actually solve completely analytically. And that's called a linear equation. So we can always solve linear differential equations, it turns out. So just imagine, we have some linear differential equation in the form of q1x times dy over dx plus a0 of x times y equal to g of x. We would like to write down this equation in standard form. By the way, this is a linear first order differential equation. Okay, we just talk about first order differential equation right now. Once everything becomes higher order, it becomes much more complicated. So we're going to derive the formula for some linear first order differential equation. So the very first step is always to write down the equation in standard form by dividing the function q1 for the y prime coefficient, if you want. And that's called the standard form. You want to make the coefficient of y prime to be 1. So if you do that, you're going to get dy over dx plus a0 of x over q1 of x times y equals g of x over q1 of x. So you just divide each term by q1x. And then you can use p of x to denote the coefficient of y, which is a0 of x over q1x, and use f of x to denote the right side, which is g of x over q1 of x. So we have the equation dy over dx plus p of x times y equal to f of x. So those functions p and f, they're arbitrary, just like the q1, a0, g. Those can be any functions of x. Okay, so the way to solve this type of equation is to try to make a full differential or derivative on the left-hand side by multiplying some function we don't know. We call it mu of x on both sides. Okay. So if you look at the left-hand side of the differential equation, we have two terms, dy over dx, that's the derivative of y, plus a function p times y. So if we would like to rewrite the left-hand side as a full derivative, then we have to connect or make connection of this form with some formulas in differentiation. And the only formula which has two terms as the derivative is the product root. Remember, when you take the derivative of a product of two functions, you get two terms. You have the derivative of each function multiplied the other function, in each term. So now, to rewrite that left-hand side as a full derivative, we try to multiply some function mu so that we can make a connection between the left-hand side of the equation with the product root. Then we can compare, those two terms with the product root. So if you do that, you're going to see we have one function mu times the derivative y plus some other function times y. Okay, so if we want this to be exactly the product root, then the second term has to be the derivative of mu times y, right? So that actually tells us that mu times p in the second term on the left has to be mu prime. If we try to construct such a full derivative. All right, so that's the whole point of multiplying this function mu. If you don't have the mu, we only have y prime plus p times y, then obviously you don't have the other function to multiply the derivative in the first term on the left. Okay, you cannot, make it a full derivative without multiplying the mu, in other words. Okay, it has to be some function times y prime plus the derivative of that function times y. Okay, so that's why we need some function mu. I don't know if that makes sense to you or not, but if you only have the y prime in the first term, then you're missing the other function. Okay, that cannot be written as a full derivative on the left hand side. So this is a trick, and that's the key step to solve this kind of equations. So we just rewrite the left hand side as the full derivative, okay, as I said. So let's suppose the left hand side is indeed the derivative of mu times y. When you use the product rule to take the derivative, you're going to get mu prime times y plus mu times y prime. Then that has to be matched with the terms on the left side in the equation. Okay, so that's just the derivative. But what we have on the left side is mu times y prime plus mu p times y. So that means, this mu p has to be mu prime. Okay, if we compare the product rule with the left side of the equation. So then we can easily find out that the mu prime has to be mu times p, okay, to make it true. Then we get another differential equation that can be easily solved by separable, equations. If you divide by mu and times dx on both sides, you're going to get a d mu with mu equals p times dx. Then you can just integrate it on both sides to find the mu. Okay, remember, mu is a function that we multiply to the original differential equation, but we don't know what mu is. We are trying to, to find such a mu that make the left-hand side a full derivative. Okay, we construct the full derivative on the left-hand side using this mu. So now we can find this mu by solving the differential equation mu prime equals p times dx. All right. So if we integrate on both sides, you get a natural log of absolute mu on the left. Okay, and you just integrate p on the right side. So that means the absolute mu has to be equal to e to the integral of p. All right. We don't have to worry about the arbitrary constant in this integral, because we only need to find one such mu that works for our strategy. So you can ignore this arbitrary constant. We only need to find one such mu. Okay. So then, once again, you don't have to worry about the absolute value on the mu, since we only need to find such one of those mu's. So you can just use the mu equals e to the integral of p. Okay, although you can also use the negative, but it really doesn't matter, because we only need to find one. That's good enough. We don't have to find all of those mu's. So then we just use this mu equals e to the integral of p. And this mu will satisfy the condition, or it will work for us that we can construct the left side of the differential equation as a full derivative by multiplying this mu on both sides of the equation. And this mu is called the integrating factor. Okay. So when you multiply this integrating factor on both sides of the original differential equation, we can solve the differential equation easily. So that's called the integrating factor. Okay. Then once we have the integrating factor, then we can solve this differential equation easily. Remember, now the left-hand side can be written as the derivative of mu times y on the left-hand side of the differential equation. On the right-hand side, we have mu times f. So we got a full derivative on the left, and we get a function mu times f as function of x. Then we just integrate the right-hand side to solve this differential equation. Okay. So let's just continue to solve the equation. That will be straightforward. Okay, what's the question? All right. Okay. David, are you able to log in? Join the session now? Any other questions, any issues? Okay, so we have the integral factor that will be, e to the integral of p. Remember, p is the coefficient for the linear term y in the original differential equation. So let's come back to the equation with mu multiplied on both sides. All right, so we choose that mu equal to e to the integral of p. so that the left-hand side can be written as the derivative of mu times y. Now, to solve this differential equation, the new equation, we just integrate on both sides. So if you do that, what you're going to get is mu times y on the left, remember? If you integrate the derivative, you get the function back itself. Okay. And on the right side, we get the integral of mu times f plus c. This time we do need to include the arbitrary constant c. Okay. So now you just divide by mu on both sides to find the solution of the original differential equation y. So y will be the integral of mu times f plus c over mu, where mu is the integral of e to the p. So it's a little more complicated, but in any case, now we have been able to solve this equation analytically. Okay. So I guess we don't have time to go through any example. We're going to do examples next time on Monday. Quite a few examples. And now it's time for the quiz. I guess I will leave you do the quiz now. Just give you a few minutes to log in. So any questions about the formulas? So we're going to start the formula next time. So this is the solution of the equation. And, we got this y equal to integral of mu times f plus c over mu, where mu is equal to e to the integral of p. So you just plug in everything to get the mu first, plug in p to integrate to get mu, and then plug in mu, and then integrate to get y, the solution. Okay, so that's how we solve a linear first order differential equation. All right, any questions at this point? If not, I'm going to stop the recording